you all the way to this. So what am I saying? This happens if and only if there is some derivative taking this guy to the limit. There's some derivative, maybe I shred this.
So,
Wait a minute, I think I'm confused.
So for our language, I guess what's going to happen, he's going to see if this is of the form of of a differential to reduce set and its prolongations, and if that differential to reduce set is coherent.
Yes.
So that would be
This is
condition for.
you're gonna see where the coherency conditions appear.
Yeah, that's
it. That's just a nice way to put it. But so you think about this order. You know, this element corresponds to this element, this element corresponds to it. They are going to be related, and this will be less than or equal to this if some derivative. Oh, shoot! I did it backwards. If some derivative of this takes you to this guy, in particular, that can only happen if the j is equal to the I. I can only take something to deal with something by differentiating if the variables are the same xi, right? So this is the way you think about this order. So basically what I'm saying here is that some leader is minimal if there is nothing, right, which is a leader, and that when I take the derivative, I get back. So this will be something like that.
So, sorry, I missed you where you start changing the definition here.
Which definition?
Well, you had a previous definition.
Yes.
Sigma comma I.
So you changed the such that, right?
I'm a little bit confused now.
He just erased what was written there.
Yeah, I just erased I just
That's changed, right?
What?
No, it's like he's just erasing.
Okay, I'm just going to erase the thing that we erased. I'm also making an aside comment on how to think about this.
Oh, so you're
It's trying to
you're just
To
making a
explain
claim
that.
that this thing
this inequality. What does it
explaining it.
mean in terms of derivatives?
To think of it, how?
Yeah.
has nothing to do with capital DK.
No, that was from the previous definition.
No.
All right.
I was wondering.
Okay, so now what I'm trying to say is what condition can we put to a tuple such that it satisfies the differential condition? So, well, I don't know if I want to talk about that because I already have like 20 minutes, right, left? Oh, that's great. That's great. Yes, okay, I'm going to skip. Okay, I'll just take it as a fact. And then I wanted to give a sketch of the argument, but I'll just take the following two facts. Fact one is, again, I have my L given in the following form. Now suppose that L is given in the following form. Yeah, okay, now I hope William is okay with what I'm writing right now. Maybe I'm a bit worried. Put a 2 now. Yeah, now I'm assuming that L is presented such a way that, I don't know, I'm going all the way to 2R. And it's going to be clear.
2R?
Yeah, it's going to be clear why I'm taking it like that. So I'm assuming this. So
R is just some fixed then.
Yeah, R is fixed.
Positive integer.
Positive integer. R is a positive integer. Suppose that suppose I have some minimal leader. So minimal leader. A, C. Suppose I have some minimal leader. Suppose that if I have a minimal leader, suppose the following, then the order of sigma is less than or equal to. So assume the following condition. I'm having this field extension such that whenever I have a minimal leader, it appears of order less than R. So in the first half of this tube. Okay?
Throughout all this, you're keeping the generators fixed?
Yes.
I mean, you can't say, well, there exists a set of generators, which this, that.
Because really the differential condition is about the tuple.
I thought it was about the field. The field is differential.
Well,
No, it
he
depends on
explained
Yeah,
that.
it's really the tuple. We should have said it on the
Because it's the
tuple.
minimal leader. Yeah.
Yeah, this is about the tuple. So I should have said the tuple satisfies the differential condition if blah blah blah. But I'm just following.
That doesn't matter. Yeah.
But yeah, it really depends on how you present L. So suppose this condition. And that L satisfies the differential condition. Then there exists a field extension, a differential field extension of K. Differential field extension of K, such that, this is differentiation, such that exactly, I don't want to say this.
Delta to the sigma of AI
Yeah, so
equals.
so the delta, I guess I can write delta K of K sigma is exactly what you would expect. This is K like this. What you would expect.
Do you mean that you mean the K to be on the field K, not to? I mean, I'm not sure.
So there is a differential field extension.
What is delta K?
Oh, it's just the derivative.
That's that K.
K is
Where
derivative, number K.
You mean this one?
Oh.
It's just a
Just a
derivative.
K derivation.
Derivation, right?
Okay.
Derivation.
For sigma
and
that
this-
is less than 2R. Or R. 2R.
Well, no, that's the hypothesis, right? So if you start with something of length 2R,
You're
and
just
satisfy
rewriting the
this condition-
hypothesis. Or what-
No, this is the conclusion. The conclusion
Okay.
is, so this hypothesis stop here. This is the end of the hypothesis. So let me remind you. I have a field of this form, and the hypotheses are that every minimal leader satisfies this condition, and that L satisfies the differential condition.
Oh, I see. So
Yeah, but if it satisfies, then you go over the derivative up to 2R minus 1.
I guess the point is that it can't be extended to a different.
Yes,
think-
yes.
yeah, the whole point is to
Oh, I
extend
didn't
it
say
all
it.
the way.
Sorry, I didn't say it. Yeah, no, you're right. Sorry.
So
Yeah,
you-
I didn't say it.
I think your notations
Yeah.
are terrible.
Sorry.
K to a K delta.
I agree.
So
I
you-
agree.
Look, I mean, when you write,
Now K delta is a
when you write
differential.
delta K,
Oh, where, oh, what's that?
Okay, but also,
yeah,
can we,
you're right, you're
can you
right.
just
What about
remind
L?
everyone, I mean, I think
I'm confused.
okay, I know what it is, but maybe not everyone does. Can you just say what K bar is in the exponent there?
So
Just
for-
to remind
He
us.
said that already.
Yeah, he said that, he said that.
Number
He just-
one
no,
is
K bar is just adding the delta Ky.
Just making sure,
But
You push up that K
You
coordinate,
said-
so to
Okay.
speak.
that A sigma
I'm
I
confused about K delta.
is a minimal leader.
You mean-
So sigma is fixed, right?
Where's
No.
As well as I.
No. I
Is
said
it
that
L anywhere?
if I have a minimal leader, so this is a hypothesis. If there
K
is a
is
minimal leader,
given different.
then this happens.
Okay.
Yeah, but.
Oh, and then the
Where
next
is
thing, the
L
sigma
in
is
that?
varying.
K delta or F delta?
Oh yeah, this thing is
Oh,
for
L's
all
contained in
sigma
F.
of order.
Really, that should be read for all sigma.
Now,
On
now
line,
then, okay, then I don't understand what the
Here,
delta
Omar,
K
all
is.
sigma.
All sigma.
Oh, delta K
2R.
is a derivative from here.
Yeah.
Okay. See, you can't tell, right?
Omar,
Yes, you
Omar,
can.
No, you can. When you use the
2R.
notation
I
A
can.
sigma
In the
plus K
conclusion.
bar sub I and
Okay.
expand
I
it,
think it's
you
2R.
also use delta K. But then that delta K is where?
Is where?
Where is that delta K?
Oh, where is it?
You're right. Sorry.
should go to 2R.
You're right.
Look.
Sorry.
Since L is not a differential field,
Yeah, right, that's what
Yes,
I'm.
2R.
and A happened to be in
Yes,
L,
I forgot. Sorry.
And
Sorry
A-
about that.
Okay.
and A happened to be
It's
in
a strict
L,
inequality. It's a strict inequality, but it goes to 2R. Yes.
since L is not a differential field,
Right,
No.
but A is in L, right?
Yes.
right.
Yes.
So what does it mean by the derivative of A?
Well,
Well,
that's,
because-
that's on a big field F.
There
You can
exists
find
a
out.
No, before you have that, before.
Okay, sure. Before I have that, sure.
No,
It
even
doesn't
in the
appear.
definition of L equals. Even in your
Oh, I
definition of L
see, I
equals.
see.
No, but that's not a
There
derivative.
is no derivative. There is no
There's
derivation.
no derivative.
But what is it?
It's just
Those
a
are
field
tuples.
extension.
Tuples of elements.
What's,
This is just a
Generators.
field extension. This is just some field extension.
Oh, okay.
that's that
All
same,
right. Oh, okay. So that was just an algebraic tuple.
Algebraic tuple. just algebraic.
No relation.
And I'm
whatever it
giving
is.
I'm giving conditions
It
with the
doesn't
two.
know, might be relations.
It might be, yeah.
Yeah, there might be. This is just
No, no,
something
I don't mean
specific.
that.
There are relations.
Yeah, priori we don't have any relations, but there may be.
Okay.
And there are two conditions, this and this. And then from these two conditions, there is that differential field extension, which agrees. So now I want to make clear, the differential condition was something like
AI
this.
signals.
The differential condition was something like this. Well, I'm going to write in that case, because we already have the two bars, so I'm going to write in that case.
Oh.
Differential
Okay, I
condition
missed-
was that there were
I
some
missed the whole
extensions.
thing.
Yeah, I missed the whole thing too.
Oh, yeah, completely. I missed it.
What do you miss?
I thought you were differentiating AI.
No.
Listing it,
First listen and then
listing
find-
it in a.
I was trying to
So
listen,
he,
but
so he listed them first
Yeah.
and then found out if it's possible to make it a
Make it
differential.
But
So
here I
you-
thought
you're
there were
taking
certain
the algebraic
number of
zeros to
derivatives
see
of
whether
AI,
it
and
is
you
a
wonder if it'd
differential
stay in
zero.
the field if you.
That's all.
Yeah, exactly.
That's all it is.
That's all it is. That's
His
all it is.
question is.
And the condition, the real condition that I'm looking for
Yeah, yeah.
Any old
is
generator.
Yes, we'll give
These are the
we'll
two
give
and
them. So
labels with
the
certain-
two
Now this
hypotheses.
labeling
that we have on
corresponds
that.
to a labeling
Right?
differential.
And the second one is there is some derivation doing
Need
this.
to
I know,
rewind.
yeah, yeah,
Need to
thanks,
rewind
I
this.
now understand it, but now I've missed half. the
Which
time.
one? So
Is it in the statement here?
yeah. So remember, the definition of satisfying the
Yeah.
differential condition is that there exists
Yeah.
I
some
see.
derivation.
Yeah, I see though, yeah.
They-
Yeah, that helps a lot.
okay,
Thank you.
right?
Yeah,
Blah, 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 blah.
yes.
And what this is saying is that in fact these guys, by the way, notice these guys, they are not derivation from a field to the same field. From some field to some field extension. What I
Yeah.
want to know is like I can lift it so that I have the same field. And this is saying, yes,
And
all the
then
way
to
to F.
interpret these as derivation.
Okay.
No, now do you?
Differential condition is it's just giving you
In the
something
big
like
field,
this.
delta K.
But the other one is telling you that you indeed
K.
can extend them.
Yeah.
More like
Oh, I see.
from all of it.
So you should think of this maybe as, just a comment, as a statement of the form, if you have a derivation and you've checked that you can extend it a certain distance,
Yeah.
then you can extend it indefinitely. Maybe, you should- maybe it
Yeah,
helps.
that's good.
I'm
yeah.
having this
Yeah,
Having
condition.
this kind
Yeah.
About having this
Yeah.
condition. So
Yeah,
this
with that.
this
Yeah.
condition, the one that I'm putting this beautiful box.
Yeah,
This is kind of saying coherency. Kind of.
yeah, it's
It's a
interesting.
little hard
Cut it in
to.
half.
It's what?
You cut it in half, the order. And when you take the coherence, you double the order.
At most. At most.
At most, it most double the order.
When
Yeah.
you check coherency, that's what happens.
It's all related to that.
So coherency, when you have something of order n,
Yeah.
checking coherency goes at most to order 2, the double order, at
Wow.
most.
Right, because you only have to
Yeah.
check their least common derivative.
Yes.
Yes, yes.
So that's at most double whatever
That's
appeared.
Okay.
That's
So
right.
that's fact 1. Now as a corollary of this fact, we have the following. I'm going to write for order 1.
Uh-huh. Oh, I see. This is getting it.
There is t, which will depend on n and m, the number of variables and the number of derivations. I'm going to do only order 1. There is t such that if I have some tuple satisfying the differential condition, I have some tuple. Then there exists. It's a very similar conclusion. Then there exists again a field extension.
I don't understand something
Let
actually.
me finish this part. It's a clear field extension. Okay, such that
Yeah, it's like a coherence condition.
I'm going to go into order 1.
It's clever.
And exactly this condition, but only to order 1. Do I want to write this? 0, this is a 0. No. Oh yeah, that's a little k. A0i. is equal to what you would expect. Okay, so what was the problem with it?
Actually, would you remind me again what leader means?
Leader means that you're algebraic over the previous ones with respect to the canonical ranking.
No, but ranking on your arbitrary algebraic tuple doesn't mean anything.
Well, remember that when I
sigma I.
remember when I gave you this,
Yeah.
and I told you this is less.
All right.
Sorry.
So you just want the
This
indexing. You just want the indexing.
You're using the same indexing.
Yeah, I think it's an,
That
yeah.
corresponds to what you were doing.
But this is really the usual rank. So now what this is saying is that I'm only looking at things of order 1.
What about the T? And
Oh.
It disappeared.
So basically what I'm saying is that there is a T which only depends on n and m, such that if I take a long enough tuple, then the order 1 part of the tuple, the first bit of the tuple, it will live inside some differential field. So such that the derivative of the zeros will correspond to the radical line. This is only order 1, but there is such a T. Okay.
Yeah.
Now, this T, this T is hard to find, right? But it only depends on those things. Okay, now, because of the time, I will only tell you how to find a bound for the T. Well, I won't tell you how to find it, I'll just give
Will
it.
you hold it? I'm catching up. Sorry,
So
I'm
you
trying
can find
to
it,
catch up.
Sorry?
It's able to, like, you're able to actually.
Yeah, you can find it. I should say that to find this T, we don't have any optimal way to find it, right?
You mean you can find an upper bound for the t, right?
Well, I mean, if you have some T, if you take something bigger, then
it will work.
it'll still work.
Yeah, it will still work. So yeah, you can find.
As long as it still satisfies the differential.
Yeah. But the point is, computing this T, we don't have a really optimal way to do it, or to even find the actual smallest. Let's call it the optimal bound. We don't have the optimal bound, but we can give some upper bounds.
Except in small values.
Except for maybe, well, even then, because the bounds that we found are for chains of finite chains, not really for.
Yeah.
You see what I'm saying?
Yeah, that's true.
So
Okay.
the way you build this guy, well, one way to build it, this guy, is by considering these things around Dixonian sequences. And we know that by Dixon's lemma there is a bound, and we know several properties about these bounds. Alexei pointed this out to us because I wasn't familiar with these things, but there's lots of work around this. How you have a Dixonian sequence, then there is a bound.
What
on the
sequence, sorry?
Dixonian.
Oh, yeah.
Dixonian.
Yeah.
Dixonian. So.
As in Grosvenor basis theory?
I think so, right?
Yes.
Yeah, there are periods there, right? Yeah.
That Dixon?
That Dixon, yes.
Okay.
So there is a bound of those. And so you use those bounds to compute
Huh.
the T. And that is
That's
why,
nice. Yeah.
that is why the T, I'm gonna erase this, the T that we need, we can take it to be, or will be bounded above by fact. And again, the arguments to show this, Alexei pointed out how to do these sort of arguments. The T that we're looking for this is the Ackermann function.
Wait, why do you have +5?
There's a deep reason why there is a
Plus
+5.
5.
Yes. We can talk about this later. I don't want to go into why there is a +5. But there is a plus. Yeah.
Oh, I thought it was.
So it's not really that great.
No, it's not really that great. So for example,
Says he's smiling.
now
Oh.
I should say
Right.
that there are
Oh.
some special cases.
Okay, yeah. Sorry.
Some
Okay.
special cases.
This doesn't apply in the case m equals 1 or 2.
when I make, no, this is just for general N and M,
Okay,
we know it's
sorry.
bounded by this.
Okay, yes.
Cases.
You see, so in the box that I was getting, I had A plus m plus 8.
M plus 8, yeah.
Well, it's better, right? A lot better.
Oh, he's still down?
So,
This is going to be computed by a computer for m equals 1, for example.
Oh, that's cute.
Okay. So yeah, this is not too bad. Well, it is pretty bad.
If you have negative 3 derivations or negative 2 derivations,
So for example,
That means
let's
we have to
do,
look at integral differential.
Really?
don't have to.
That's good. I'd like to hear that. N equals 1.
N equals 1. So in the N equals 1, there we
Wow,
can actually find
Good to
out.
know, too.
I mean, this is
That's
a
where
this is
Red
a
lives,
special case.
really.
This is not awesome. This is some special case.
N times N.
And of course, now it's
Three.
great for 1. So
Yay.
But
This is two.
no, but it's more impressive. I think the m equals 2 cases.
yeah. So let's go into
More
that. Some special case.
So
N
when
equals
m,
one, M equals
when m
two.
also equals 1, you would just A four 3, right?
You can take
That's
this
not that bad.
to be 1. You can take it to be 1 and everything
You
works.
still can't compute.
Okay? When only one derivation,
Uh-huh.
I can just tell you, define it to be 1.
Wow.
Just define, oh, it should be a 1.
1.
Just define it to be 1. Okay? Because this condition will work.
that's nice.
Yeah.
Yes, so this will be 1.
Sure.
The other one is what James is saying, that we have some
M
control.
equal 2. Yay, we like that one.
Okay, let's see if I can. Again, this will be bounded by
Equation.
what? Let's see if I can do this. 2 to the bn plus 1, where, what is
It's
bn?
BN.
b0, I will forget it's b0 is 1, 0 or 1, sorry. Let's forget which one is.
Huh.
b0 is 0. So this is a recursive definition of bn is equal to 2 to the bn plus 1. Sorry. bn plus 1. bn plus 1. Is that right?
No, I think because you can't have that. I don't
No.
think because
This is, I'm sorry. Sorry.
but what is no because you have a
Wait.
bn in the exponent. You
Yeah.
mean bi
Yeah.
plus 1. So I'm just making sure people can see that in the exponent of 2.
There's a bn plus 1.
No, over there.
Over there.
The plus 1 is not in the subscript.
Oh, no.
No, I mean to the right of where you're right.
Over there.
Yeah.
Define
It's on the same
No,
level.
the n should be I.
Yeah, it's bn plus 1. Not-
BN plus, like
Okay,
that.
Yes,
So-
yes.
sorry.
Sorry, I'm just making
Yeah,
sure
no, you're
it's
right, you're right. Good.
visible.
Okay, so the two cases, you can take it to be at most, you can take it to be this, but it will doesn't equal.
Would be B.
2 to the bn plus 1, where bn is defined recursively with this formula. So it will be a tower of
Yeah,
exponentials
Yeah.
Of length at
length
most
n.
n plus.
and plus some
One or
I
something,
guess,
yeah.
at most 2n, of length at most 2n, right? The length of the exponential will be at most.
It'll certainly be bounded by that.
Yeah, we got that. But this one you can compute, this is not too bad.
That's not too bad.
This is not too bad.
Is it 2?
And it's just the number of variables as well. So if
Yeah,
the number
yeah.
of variables is
Ah, you can do it, right?
low,
Yeah, so what happens
Yeah.
if the number of variables, let's do it, it should be easy. What is, yeah, if it's low, it's variable. So what happens when it's 1?
Yeah.
You should be able to do this, right? Let's do it.
so
B1, 2.
So you just get b1, right?
Mm-hmm.
So 2 to the b1 plus 1, but b1 is simply,
plus
What?
plus 1 you need after, not in the exponent. There's a plus 1.
oh, sorry.
Yeah, because
No,
the bi is 0, but sorry.
So this one, I'm just saying that the TBN will be the 2 to the b1.
Oh, yeah.
Oh,
but
yeah,
now
yeah.
to
Yeah.
compute the b1,
Okay, now
b0
yeah.
is 0, b1
Sorry.
will be 2,
To the
To-
1
to-
plus 1, 3.
2, so 3.
3.
And then plus this one. 4. Right?
Yeah.
4. Oh, that's impressive.
This is not too bad.
So it's
right?
only 8.
This is not too bad.
2 to
16.
I mean, you
4?
can do it for a couple of
16.
Yeah. That's not
Let's
bad.
see if I got this number
Compared
here,
to
because
that.
I actually did a coupling here. You did good. Yes, 2 to the 4. And if you do, maybe I can tell you. I'm ready here. I told people else. What happens if you do 2, 2? I did it in West.
2, 2.
Did it. What?
Yeah.
Not too bad.
That's not too bad.
But then after 3, then it's
Too
bad.
bad. No
Do you know
factorials.
how sharp these bounds are? Like this special case for like n2.
So this bound, in terms of the Dixonian sequences and all that, for the case of m equals 2, this is sharp.
Yeah.
for the Dixonian
Sharp mean?
lemma.
It means
For the
that
bounds of
it means
Dixonian
that there
sequences.
are
However, we don't know
solutions
for
to
the
the
bounds
combinatorial
in
problem
these
which
differential
require
conditions.
you to go.
Oh, okay.
So in general,
so-
the bounds
Yeah.
the Dixonian's lemma
That's one of
gives
the
you will be
combinatorial
larger
problem.
than
If you can
the
discover a
sharp bound
better
here.
factor
But for
of
Dixon's
differential
lemma,
algebra,
this is
Right.
sharp. For the case of
Yeah,
Maybe
that's
proof.
very interesting.
So, could you give an example of a sequence of length 4?
A sequence. Yeah, by the way, when I say Dixon lemma, I don't really mean Dixonian sequences. I mean this is a sharp bond for sequences of anti-chains.
So, could you...
Yes.
Well,
For sequences of anti-chains. So the most basic sequence of anti-chain. So for example, why is this? The reason this case is so well behaved, this is the case of m equals 2, is super well behaved.
yeah.
This is super well behaved.
Yeah,
This is
that's
all the
interesting
following.
conceptually.
This is super well behaved. Why? Because
this is nice.
if I have, for example, whatever, 3,2, right? 3,2. Then I can take, by the way, this, of course, whatever, this is 5, right? Right? Now take S5 to be the simplex in R2 of, how do you call it, the simplex of 5. What do I mean by this?
The diagonal that goes through the points
Yeah.
that are on
Yeah.
the line from 0, 5 to 5, 0.
Oh, okay.
Yes. So maybe 2, 3 is in here. 3, 2. So I take all of the ones that are. So by the way, here I get it's 6, right? I get 6 points, right?
On that line, yeah.
1, 2, 3, 1, 2, 3.
Yeah.
6 points. So this has 6 points. So this, for example, would be an example of a sequence of anti-chains. These elements are incomparable in the order I told you.
Yeah, yeah.
And this is in particular a Dixonian sequence as well. But of course, Dixonian sequences are larger in general. But I'm just worrying about things that are
So, what
incomparable.
about 4?
Oh, this one.
Yeah.
Oh, okay,
Could you
let's
state
see.
this 4?
So what did I do here? Two derivations, one variable, right?
Yeah.
Oh, because it should be. This is why. Because in that guy, the most I can take is 2.
No.
So, could you explain?
Pardon me? What
Yes.
you-
So in order to compute this guy, I take 2 to the largest one.
Yeah, so how many do you have? Why do you have 4?
I should get 4, right?
Why 4?
Why should I get 4 or why do I get 4?
Why do you get 4?
Why do you get 4? Okay, because notice that what I didn't say is that in the sequences that I'm interested, so suppose I have a sequence, right? Dixonian or
Whatever,
incomparable, such that in my sequence I want this.
Yeah. So, could
Right?
you give an
So
example?
for
of the
example,
sequence of this
my first element in my sequence,
Yeah.
right? So for example, this can happen, maybe 2, 0.
Yes, and what's next?
Now, what is the longest chain that I can build?
Yes.
It's 2, 0. Then what's next? 1, 1.
Yeah.
So 3, right?
So 3.
3 points.
Oh, that's
How
better.
do you have 4?
This is the 3 is Bn. So it's, remember, my bound is 2 to the Bn plus 1. My
What
Bn
is
is.
the plus 1 from?
Oh, because this means that there is an actual sequence of length 3. What I want is a sequence, right? Which, okay, how do I say this? I want one more. In order for my arguments to work, I want a chain which is not properly increasing. You see what I'm trying to say?
No.
I want a chain. So what I'm saying is that indeed in this case, the longest one I can get is 3. The
Yes.
longest one I can get is 3. But for the arguments for the proofs, you want to take one more such that you get a repetition. So that you get something which is not an anti-chain. So the smallest the smallest number, such that you are going to get something that is not an anti-chain.
Okay.
So this is why you need one more. So with one more, you know that this cannot possibly happen, because if I take this 3 and I add one more, whatever I put it,
Yeah.
is going to be comparable to something else. That's what I need the plus 1 here. So I get 3 plus 1, 4, and then I take 2. Was that? I just need to take something that makes it not an anti-chain. That's what I need to do.
So would this argument work when n is 3, but now you're in free space? Or is it
So if
Oh,
n,
that always
if n is 3,
to 3
so for example,
space.
you will get to here, right? And then this guy has order at most 2 to the 4, right? So now, once you have this 3, well, now you have to put, for example, 4 0. And then you count.
Can I just make a remark on why it seems like to me, and this isn't very rigorous, why it seems like the case m equals 2 and n equals 1 is much different than the higher cases. To me, it seems different because because of the fact that once you pick the first element of the anti-chain, you already, even if you picked like whatever control function you wanted instead of 2 to the I, you already have a bound on how big that chain of anti-chains could be without thinking at all about the growth of the size of the element.
Exactly.
And so those other cases, you kind of have a trade-off because you have to think, well, I'm picking these lattice points, I can pick them in different indices, but the farther I go along, the more growth I can have in the norm, or what we're calling a norm. So you sort of have to pick more carefully, whereas in this case, you don't have to be so careful because the function doesn't matter.
So this is what James is saying, that once you have an element in your sequence, then the length of your sequence would be bounded by this.
Yeah.
In n equals 2, m equals 2.
M equals 2. But this doesn't happen when m equals 3 or more.
For
You may want to take a look at my
for
I was thinking of you.
m and n equals 2, do you have a sharp bound?
I was thinking
For which values are?
I don't think we've worked that out.
m equals n equals 2.
m
Both
equals
of
n
them
equals
equal.
2.
Yes, do you have a sharp?
I don't think we worked that out.
Sharp bound for the, I mean, for the sequences of anti-chains, we do, of course. But
We do.
Which is what?
which is this.
Yes, sorry.
This is a sharp bound.
Yeah.
So this bound without broken,
So
for n
familiar.
equals 2 and arbitrary
We were going over
n,
that
this is sharp for
city.
every n. Okay, this bound that I have here for
I
anti-chains.
think you may want to
sharp.
take a look at the well-ordering theorem and the proof, because we are. So again, you start with some point, and then you start bounding the second coefficient and so on and so forth. And I think that might give you this bound on t, which is a lot smaller than the Ackman function.
Much smaller. Okay. Okay.
Oh.
Wait. What do you think? Can you say?
I'm making up
Almost
guesses.
back.
Okay.
Okay.
Sorry. So can I say something about that?
Yeah.
If what you're looking for are bounds for this type of sequence, anti-chains, then no. A lower bound is the Ackermann function. A lower bound is the Ackermann.
So you don't think there is some projection between anti-chains and dimension polynomials?
I don't know. I mean, so
Or rather initial
No.
sets. Actually, rather initial sets.
Initial sets.
I don't know.
I think it has something to
No,
do with it.
because, I mean, no, this is for sure true. This is for sure
Because
true.
basically, what you're trying to do in your generation of L is you're taking some initial sets, right?
Yeah. So in the generation of L,
Yeah.
those bounds they might be smaller
Right.
than the Ackermann function
Yeah.
for sure. Those ones,
Yeah,
yes.
that's what I'm saying.
For the anti-chain sequences, then no.
And no.
Because you see, it's two different bounds. One thing is for the
That's
differential
true.
condition, the one is for these anti-chains.
That's true. yeah.
For anti-chains, it won't be less than
I
it
see.
won't be less than a to the m 1.
Right, that's
Two
true.
or
That's
something.
true.
I
That's
can't
true.
remember.
Yeah, right.
This is
Yeah.
There are more combinatorics in there.
So yeah, what I was saying for m equals 2.
Yeah,
this-
yeah.
So, and that number is equal to what?
So this. By the way, again, this is a sharp
But every-
bound for
no,
the
but
chain
every
for the
anti-chain-
sequences of anti-chains.
But every anti-chain gives you an
It's
initial
2 to
set.
the bn plus 1,
Can't understand.
where the bn is defined this
Isn't
way.
it true?
So what will be for a tutu?
Can I? So
Isn't it true
You
that
say
every
that,
sorry.
You have to wait.
you're basically saying that Bn is a sharp bound for the length of the anti-chains.
Yes,
That's what you're saying.
that's exactly what I'm saying.
So when m and n are both 2,
Yes.
you said that T22 was 2 to the 2 to the 4th plus 5. That's what you wrote down.
Right, yeah. Mhm, yeah.
So for that one, this is the one you want, right?
Yeah, so B2 would then be 2 to the 4th plus 4.
That's right. 2 to the 4 plus 1.
Plus, I'm not very, let me just do it because I get really confused about these things.
2 to the 2 to the 4
2
plus
to the B1 plus 1 plus B1 plus
Yeah,
1,
you have to
right?
write it out.
And then we completed B1 to B3,
There it is.
right? It was 3, right?
Yeah.
So, thank you. Yes, I just need to do it.
Okay.
Yeah, so that is the,
So you're saying that when M and N are both 2, there is an anti-chain of like 2 to the 4th plus 1.
the length of anti-chain, right?
So 2 to the 21.
This is the longest
Oh,
length.
right.
This is not
Chain
Simon,
of
this is-
anti-chain.
Could you give an example of how it could be at least of close to
Yes.
the length?
Yeah, no, this is simple. This is this generator what I was doing over here.
But isn't it true that for every anti-chain that you give, that there is an initial set corresponding to it?
So
It defines a,
Yes.
Underneath, the-
yeah,
Yes.
on the stairs.
underneath
Right.
the stairs.
But I
we're
mean,
taking
So the number of it would
N
be
equals 2, N
related
equals
to the
2. So-
number of dimension polynomials.
0, 1, and then what is this? CO2, right? So here I have 3, right?
Yeah.
Maybe.
And then I move to the second n, right? I'm thinking of n. This is n to the 2.
And I understand now.
You understand now?
Yeah,
This is-
yeah,
this
because
is-
you passed 3 steps
Yes,
and you already
yes.
allow yourself a higher order.
Exactly. So
Yeah.
here I can take
Mhm.
He goes under it.
1, 2, 3, 4, right?
Yeah, it's clear now.
And then I complete.
Yeah.
But why you had to the 4? Because it's
I
4
would
step.
think
Okay,
it's an
so-
initial
okay,
set. I
now
don't
it's
see
clear.
why there isn't that.
Was that?
Yeah,
I'm
yeah,
not seeing.
hmm.
What's an anti-chain? It's just the
It's a set of
uncoupled ones.
incomparable elements.
Yeah.
Right, that's it.
That's an initial set
So that always
underneath the
defines,
stair.
that's a one-to-one bijective corresponding to initial set.
Yeah,
Yeah. Yeah.
Right?
That's
yeah.
right.
So,
But still, I mean, the Ackermann function will be lower bound.
but you're actually counting the number of initial sets.
Yeah,
then.
that's, oh,
It's not just, okay.
okay. Oh, okay.
Okay, now I want to finish. So, sorry, I don't have more questions about this. I just want to finish with 2 statements. If that's
You
okay
have a
with
way of
people.
doing that.
Yeah. So we should finish.
Not sure.
about
You might.
3 minutes.
3 minutes, okay.
Sure.
So I'm going to finish with the following
Look
2
at that.
statements. So, but I mean, I can answer more questions
I
about
mean, I
this.
didn't really count
bounds.
it, but
Yeah.
it doesn't seem
No more.
that bound should be.
Oh, I raised the fact. I left it there for the whole talk and I was exactly what I wanted. I raised it. Well, you guys remember this.
Sure.
Okay, another is, so remember, this thing was something like, something projects dominantly, then the sharp points is dense. There was
Right,
something.
right.
Oh, yeah, yeah, that,
But I said that in the partial case, this is not true.
right.
But now, an analogous statement is something
That
like
was
this.
vivid.
I have B and I have W. These are given, B and W, these are given,
Mm-hmm.
right? Now suppose there exists an X, a subvariety of B, T, and M, so that the T is the T we've been talking about all these 15 minutes.
Oh, you have to go that far. I see. I see. I can
Well,
find
you
the
don't
picture
have to,
on
but
it.
you know that it's
No, but just so I can see the
Just let you
picture.
go a bit far.
Yeah.
Going that
You
far
don't
is
have to
good
go any
enough.
further.
Exactly. So by the way, since I have my N and M fixed, I'm gonna delete this just because it's
Yeah.
N and M. So I have some subvariety contained here, such that what happens? Suppose it's right with the following: B, T minus 1. This is a bit messy, so I'm just gonna write the statement. Don't worry so much about,
Mm-hmm.
you know, these projects dominantly onto X. Then, and X,
Also goes from far.
this projects dominantly, and also X projects dominantly onto V. So these two conditions. There are two maps projecting dominantly here. These two conditions, then I can conclude exactly what I said before. Basically, what I'm doing here,
By dense, you mean dense in V. Dense in V.
In V.
V, yes.
Yeah.
This is a
Okay.
subset of V, right?
Yeah.
Oh, wait.
So.
Oh, yes, it's a
This,
set of all x, b.
this is the set of all x and b, such that
Yeah.
the derivatives, they
Is
lie
it
in W.
The, yeah, gradient isn't,
The nabla,
so to speak.
the nabla mablans in W.
Yeah, yeah.
Basically, this condition, this dominant business, is more or less saying satisfies the differential condition.
Yeah.
That's why I need a T. So I have some sort of differential condition going on here. And that allows me to conclude that I get a lot of points. Okay, so I'm not going to go through this, but this is essentially an application of the bound T and the differential condition and all that. Okay, now what do I get out of this? Well, I get the following. I'm going to finish with this. So remember, I'm assuming this guy is finite, right? And what I'm trying to say is I'm counting number of points, counting points. And then I want to give you the promised bound, which I can never remember. It's a very long bound. There we go. Degree of b to what power? To the power of same number. Where, of course, d is the dimension of b. What is this row business? Alpha t minus 1 minus 1. By the way, I should say, James, there used to be a +1 here.
Yes.
I noticed that. You can get rid of it.
I see. Okay.
Why? I worked. You were gonna complain about the one. I know you would have James is gonna be like, there was a 1 there. What's wrong with you? No, I worked kind of hard to get rid of that 1. Why? Without that 1, if you take one derivation, and of course we said that in one derivation the t was equal to 1. This big mess reduces to the one that I stated with the ordinary case, which was very simple, right? It was 2 to the d minus 1. So once I get rid of that 1, then this reduces to the ordinary case. But this is the bound, and something that you can know from this bound is that if we fix, all the data except the degrees, the degree does not appear in the exponent. So it changes polynomial in the degree. And in fact, this is not too bad. The only bad thing is the t. If the t is very large, then that's too bad. Right? If the t is not too large, then this is not too large.
Get these super
What's the alpha t?
Oh.
Oh, right. It's I forgot about that. Okay.
Very good.
Yeah, okay, yeah.
It looks like fun.
That's a huge number when t is big, right?
That's the problem.
That might not be.